Hello, welcome to part 2 of lesson 1 for CE3372 Water Systems Design, Fall of 2020. On the screen I have navigated to the course content page via an internet browser, and we're now going to select lessons from the navigation tab and Distribution System Lesson 1. And in the notes section, there are the lesson notes, and there's 3 readings. Part 2, which is what we're doing right now, is associated with those readings. And the topic of Part 2 are types of water systems. And so let's look at these 3 bullet items. Water systems are classified as water control systems, or systems that are used to control water. Water use systems, which are systems that are used to provide water for our use and remove wastewater after use. And then a last one, environmental restoration systems, are a water system that's designed to provide some benefit to the environment in some context external from human drinking water or wastewater use. And here are classifications of water control system. We're going to leave this slide shortly and go into the readings and see what we can learn from the readings. But as I go through some of the selected readings, bear in mind that control usually means something that's designed to cope with the spatial and temporal distribution of surface runoff from precipitation events. Drainage engineering, if you will. So flood control systems, storm water control systems are clearly in the water control category. Stormwater harvesting, which actually most of our surface drinking water is at some scale stormwater harvesting, but here it's a control system. And the main technological metric on sizing them is based on the area that has to be served. So the larger the area, the greater the quantity of water that has to be controlled. Let's go take a look at some of the readings and see if we can learn anything from that. So I'm going to intentionally choose the readings from Chin first. I'm going to download the file. Okay, show in the Finder. And I'm going to actually open it with a particular software so I have some ability to make markup. Open with the graphic converter. So this is going to open the file as just a series of pictures. But I have a writing stick, and I think I'll choose yellow. And we can use that to underline things. So let's read chapter 1 of Chin's book, or at least an excerpt from. It starts off with water resources engineering is concerned with analysis and design of systems to control the quality, quantity, timing, and distribution of water to meet the needs of human habitation and the environment. So some of those keywords that were appearing in the bullet item. Let's go back to the notes and take a look at that. And then it goes on to give a fairly brief review of the concept of hydrology and how it relates to water, and then some of the main technological issues in water resources: subsurface, surface water, chemistry, geomorphology control, and policy, economics. And they're all equally relevant. And that's about all we'll get out of this page. So let's move on to the next page. On the next page, presents a list of United States government agencies that are primarily involved with water engineering. And in no particular order, the United States Geological Survey, the National Climatic Data Center, Bureau of Reclamation west of the Mississippi, the east of the Mississippi is largely Corps of Engineers country, although they work out west too, as does the Bureau of Reclamation work in the east. The Environmental Protection Agency and the Natural Resources Conservation Service. There are others, of course, but these are large government agencies that are arguably directly involved with water and ultimately water systems design. The next section is the hydrologic cycle, which you would have had. Consider that review of hydrology. And then he presents a table where he looks at contamination of water and has a series of different examples. I want to return to this one. Then there's a table of world water quantities from the 70s, and there's no reason to believe that the proportions have changed very much, and certainly the Union of Soviet Socialist Republics was more than capable of producing a tabulation like this. They also looked at the different components of the hydrologic cycle and the fluxes in the different parts, and the average precipitation, evaporation, runoff to ocean in millimeters per year, which at first glance might be a weird unit, but when you multiply that by the contributing area, you get volumes. And then we get to water resource systems. Let's pick a better color than use purple. Since we're dealing with rain, purple rain. Then we look at the design of water systems, which is what this class is. Certainly, that's in the title. There is frequency-based, risk-based, and critical event. And in frequency-based, the exceedance probability of the design event is selected in advance, and then the water resources system is designed to accommodate that particular event or lesser events. And that's pretty common in municipal engineering for stormwater collection. For drinking water supply, that's actually a different category. That's a use category, not a control system category. We're interested in the customers we have to serve. But very similar. We come up with a most probable, if you will, demand, and then we design our system to satisfy that demand. When we get to the next one, risk-based design is quite similar, except instead of explicitly stating the event magnitude a priori, a particular risk or probability is stated, and then the design is evaluated to meet that risk in some sort of a failure mode. And then the last one is the critical event design, and that's often used for cases where the consequences of failure are catastrophic. So an example of that, where there was a failure would be the nuclear power plant operated by the Tokyo Electric Power Company that in 2014 was hit by a tsunami, and it damaged the cooling pumps, and there was a large radioactive release. So the tsunami killed a lot of people in and of itself. The radioactive release pretty much damaged a large area of Japan that's currently not habitable. A tsunami hitting in Japan is a predictable event. Hitting the power plant and the power plant having to provide its own pumping capacity was a predictable event for whatever reason. Possibly not even malicious. Those two never got put together, so it was never considered in the design. Had it been considered in the design, it's quite likely that power plant would still be making electricity today. So here's where I want to get to. So there's water resources system are categorized as water control or water use, and then the third category is environmental restoration systems. So let's move to table 1.6, next page, and you'll see where those things come from. So here the author has described water control and water use systems. So water control systems are designed to control the spatial and temporal distribution of surface runoff. Example are floods, floodplains, and so on. And at the end of this section, the author provides some contextual examples of water control systems. Water use systems are the other things that we are involved with as civil engineers, and actually in some contexts slightly more important, very slightly, than a control system, because these are used to provide the water that we need for our everyday activities of living. So water use systems include water treatment, water distribution, wastewater collection, and wastewater treatment. In this class, we won't spend much, if any, time on water treatment or wastewater treatment, other than they will be a source point or a sink point for our other components of water systems. That's because these are covered in other courses that are required in the environmental engineering courses. You'll get more direct information on these too. We will focus to some extent on water distribution systems and collection systems. So wastewater collection system is not much different than a stormwater collection system, except the volume is far more predictable. So this class will spend a lot of time on water distribution and stormwater collection, and a little bit at the end on wastewater collection. The reason for the wastewater collection lower emphasis, we'll put more effort in stormwater collection. The hydraulics of the two are similar enough that studying one confers knowledge on how to design the other. So water distribution systems, which will be the first part that we talk about, have to deliver demand while sustaining water pressure, and collection systems have to have sufficient capacity to transport water without overflowing into the streets. And that concludes about all we need out of this reading. We'll go to the next page just to be sure. Not much there, and done. Okay, so now if we return to our presentation, we have summarized water control as per Chin, and the key idea is that the capacity, they get sized based on the area that they have to serve. We move to water use systems. We saw at the end of that rating that it had to do with water that's in support of human habitation, so water supply, treatment, and distribution, wastewater collection, treatment, and discharge. And the key idea here is capacity is based on population served. And these designs are hydraulically dominated, meaning that the hydraulics plays a big role in the design, and because the population and capacity are somewhat directly correlated, the area is irrelevant in the sense that it doesn't make much of a difference in the demand. In the case of control systems, those are hydrologically dominated because of this dependence on area. And then to complete the discussion, I have a little bit of bullet item on an environmental restoration system, and these are described to some extent in Mays. Right here, where he describes environmental restoration, and I think the rest of this is mostly history, and then water use in the United States. Yeah, there's not a whole lot on restoration from a concise context. So let's return to the presentation. If you read May's book and some others, you probably will conclude that restoration systems are systems that are designed to manage the spatial and temporal distribution of water in support of non-human habitation. And the goal is to create desirable conditions for some species or some category of species. The word desirable is a value judgment, so that implies that a policy has to be stated, and that would lead to desirable conditions. Once the policy is stated, the technical design is straightforward because we know what desirable conditions are based on policy, and we can build engineering projects to create desirable conditions. An example of that would be building a national wildlife reserve where your goal is to produce sufficient wetlands to grow ducks, because you've made a value judgment that ducks are a good thing for society to have, and people who like to hunt ducks can go out with their slingshots, and if there's more ducks, they have a better hunting experience. Doesn't end too good for the duck, actually, and that would be desirable. Once that policy is set, designing such a wetland system is to some extent straightforward. And that pretty much concludes part 2 of lesson 1, just our introductory lesson in water systems design. We won't focus very much at all on environmental restoration systems. The bulk of this course is spent a lot of time on water use and a fair amount of time on water control in the context of drainage engineering.